Hi, y'all. It's Mrs. Blasky. Today's video, we're going to talk about topic 0.5, which is about, we're going to sort of mush a whole bunch of stuff together. We're going to talk about mass percent, we're going to talk about empirical molecular formulas, and about how mass spectrometers work. Mass spectrometers are a piece of equipment that no high school lab is ever going to have because they are giant and expensive. But the information that they share with us is really important. We're going to talk about a couple times throughout the year. So a mass spectrometer, or sometimes we call it a mass spec, is a piece of equipment that we use to figure out what an unknown is made of. There's a couple different ways to do this. One way that we'll talk about later is about taking a specific element and seeing how many isotopes it has or what the masses of those isotopes are. Another way that we're going to talk about today is about identifying an unknown chemical to figure out what elements is it made of and in what ratio are those elements. So here we have a quick picture of sort of what happens inside a mass spectrometer. This isn't what it actually looks like. It's really in a giant box with computers and all kinds of fancy technology hooked up to it. So what you do is you take a sample and you put it in here, and there is, depending on what type of mass spectrometry you're doing, there is some sort of device that heats up, that splits apart, that vaporizes that sample to break it apart into its atoms. Now, those atoms are sent through a curved tube. Oftentimes it has a magnet on it. That magnet helps separate out positive and negative ions if we have an ionic compound. And the curve in the tube helps separate out things by mass, which is why it's called a mass spectrometer. If you think about driving in your car and you take a turn really fast, you can feel the force that your body takes by going around that curve. Now, your body might move a little bit in the seat as you take that curve really fast, but if you've got your backpack in the back seat, it's going to roll over. If you've got a Coke bottle or a can rolling around, it's going to go even farther because it weighs less, it has less mass than your body or your backpack or the car itself. So things that are very small get flung around this corner faster. Things that are larger, that are more massive, don't get flung as far as it goes around the corner. So those particles get separated out, or as we say, deflected. As they come through, there's a detector at the end that figures out how many of each particle are hitting that detector at what mass each one of those are. And it spits out a graph or some data or some sort of information to tell us what's going on inside of that particle. These pieces of equipment get used a lot to identify if a chemical is what we want it to be. People who work down at Lilly or at Dow or at some of the other big chemical companies, if they're trying to design a specific molecule for medicine or for equipment or for materials, they can do this and see, well, did we actually get the molecule that we expected to get from our experiments? We can also use this to identify unknown materials that are found. If people who do forensics, like CSI people, if they get a sample from blood and they want to know what drug somebody overdosed off of, they can do this type of experiment to figure out what that substance was. So it's really important, and it's a really useful piece of equipment to use. Now, the information that that mass spec gives out can be different, but usually what it gives out is a percent composition. So it will say the sample that was in here was 22% carbon and 78% hydrogen. And so what that tells us is the percent composition of each of those elements. So it says if I'm 22% carbon, it means that 22 out of every 100 grams of sample was carbon. And if it's 78% hydrogen, then 78 out of 100 grams of that sample was hydrogen. Based on those percent compositions, because we know that elements combine in specific ratios, that's one of our laws of chemistry, the law of composition, we know that every formula is always going to have the same percent compositions. So if I have something like this copper bromide, for every molecule of copper bromide, there's 1 part copper and 2 parts bromine. But copper and bromine have different molar masses. And so it's not just always that it's a 1-to-2 ratio. We have to identify what that ratio is going to be or what that percent is going to be based on their mass. So if we go to our periodic table, we find copper, molar mass is 63.55. So 63.55 for copper plus 2 bromines. Molar mass of bromine over here, 79.90. That will give us our overall molar mass of this compound. Had to go grab my calculator real quick. If you add those together, you get a total mass of 223.35 grams per mole for copper bromide, copper 2 bromide, right? So if we want to know the percent copper, we take just the mass of the copper, which is 63.55, divided by the total molar mass, which is 223.35. Good, and put our units on here. So 63.55 divided by 223.35 times 100 to give me a percent, gives me that copper is 28.45% of the mass of that compound. Now, to find the percent bromine, we could go ahead and do this and say, well, there's 2 bromines, each one is 79.90 grams per mole out of the total molar mass, which is 223.35 grams per mole. We could do that math, or we could just take it and subtract it from 100. Take that 28.45 from 100, and we would get 71.55%. Right? Those percentages should always add up to 100. Now, if you're doing calculations, like for something like this ammonium sulfide, we've got more than one element, or more than 2 elements, and you're going to have to do multiple calculations. Rounding might get you a little funky. You might get 99.99%. You might get 100.01%. That's okay. Don't stress about that. Okay. So those percent compositions, if we know our formula, we can get to the percent composition. We also, if we know the percents, can get to the empirical formula. Now, I'm going to do one of these examples together because this is something that people always forget how to do, but this is something that you need to practice. These show up on the AP test all the time, right? So here we've got nicotine as an example, 74.2% carbon, 8.64% hydrogen, and 17.2% nitrogen by mass. Find its empirical formula. When we're finding the empirical formula, we're really finding that ratio of atoms. How many of those atoms are there to each other? In copper bromine, it was 1 copper to 2 bromine. We need to figure out what the ratio of carbon to hydrogen to nitrogen is. So to do this, I'm going to give myself a little bit more room. If they give you percents, we can just pretend that those are grams and say, well, what if we have a 100-gram sample? 74.2% of 100 is 74.2 grams. And that's our carbon. We're going to do a little dimensional analysis. We want to turn this into moles because we know all of these elements have different masses. What really depends is their molar mass and how many moles we have. That's what we can actually compare. So 74.2 grams. Carbon 12.01 grams of carbon is 1 mole. I guess I didn't need that much space. We need to do this to all of them, to all of the elements in our mixture. So 8.62 grams of hydrogen, 1.008 grams of hydrogen is 1 mole of hydrogen. Evidently, I need even more room. And 17.2 grams of nitrogen, 1 mole of nitrogen is 14.01 grams. So we crank through the math on this, 74.2 divided by 12.01. When we do this math, don't round off. Don't be ridiculous and keep 400 digits. Keep a couple extra just to be safe. Only because it's going to help our answers be a little bit more precise in the end. For nitrogen, I got 1.22769. Now this is moles. Please make sure you label all these so that you can keep everything straight. Now, I could write that it's a ratio of 6.178 moles of carbon to 8.611 moles of hydrogen to 1.22 blah, blah, moles of nitrogen. That doesn't mean anything, though. That doesn't get us to a formula. To be able to get to a formula, we need whole number ratios. That's how atoms combine. Atoms always combine in whole number ratios. So to get the whole number ratio, we take from these moles, we find which one is the smallest, and we divide all of them by that smallest. That means that we're guaranteed to have one atom that's a 1, and the other ones will scale up from that. So if I divide everything by this 1.22769, handwriting is never very neat on the computers. So that ratio is going to be 1. It means guaranteed in my formula, I'm going to have 1 nitrogen. So now if I take the 8.61138, I'm going backwards, divided by 1.22769 for the hydrogen. That gives me 7.01. That's pretty much 7. That's why we wanted to keep these numbers with as many decimal points as possible, because it would help us get as close to that whole number as possible. And then we do carbon, 6.17818 divided by 1.22769 gets me 5.03. That's basically 5. So to write my empirical formula, I have 5 carbons, I have 7 hydrogens, and I have 1 nitrogen. So that is the simplest ratio of those elements to form this compound nicotine. Is that actually its formula? We don't know. It could be twice that big. It could be 40 times that big. But we know that that's the ratio of those elements. If we want to figure out what the real formula is, or what is called the molecular formula, we need one other piece of information. We need to know the molecule's actual molar mass. So in example 18, it tells us that the molar mass is around 160 grams per mole. Let's compare what our empirical formula's molar mass is. So 5 carbons is 12.01. 7 hydrogens, each one is 1.008. 1 nitrogen, which is 14.01. We add all those together. Let's see what it comes out to be. That molar mass of our empirical formula is 81.116. So now comparing that to what the real molar mass should be, mine is about 81. They said it's around 160. Lots of times they don't give you the exact molar mass. They just give you an estimate. I'm about half of what that molar mass should be. If I double my formula, that's also going to double my molar mass. So to be able to get a molar mass of around 160, I need to double my empirical formula. So instead of C5, it's going to be C10. That's messy. Let's rewrite that. C. Instead of H7, it's going to be H14. Instead of N1, it's going to be N2. That is our real formula, or our molecular formula. Now, it doesn't tell us how it's bonded. It doesn't tell us what its structure is. We'll get to all that mess later. But it does tell me what the formula is from this percent mass data, which could come from a mass spectrometer. So again, there's a couple more example problems down here that you can try out. Give that a try. Make sure you get this pattern down. We will be practicing this in class a little bit more also. But this is something that does show up on AP questions. So make sure that you can handle this. If you've got any other questions, let me know. I will see y'all later. Bye for now.